Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Our objective is to take a brief look at the relay. A relay is an electromechanical switch that serves as the principal logical element for an electrically controlled system. In contrast to the contactor, a relay is traditionally designed to establish or interrupt low voltage control or pilot signals only, and not high voltage, high current power input used to run an industrial motor. Relay contacts seldom directly switch primary loads like motors or pumps, and only do so in the lowest of low-power applications. Relays typically switch pilot or control signals to other pilot devices like the coils of contactors or the solenoids of hydraulic valves. Devices like contactors or solenoids, when commanded to do so by the pilot signal, do the actual conduction of primary electrical or hydraulic power. Similar to the relay's big brother, the contactor, a relay also has a coil and associated contacts. The principal difference being these contacts are traditionally rated for low voltage control signals only. Relays are used in applications when it is necessary to control a circuit with a low voltage control signal with complete electrical isolation between the control and power aspects of the system, or where several circuits must be controlled by one signal. Relays can perform numerous functions and coordinate the activity of a complex system because a relay traditionally has available not only normally open contacts that close when the coil is energized, but also normally closed contacts that open when the coil is energized. These contacts can be used within the logical framework of an electrically controlled system to selectively energize or de-energize other elements within the system or between two separate systems at the appropriate moments to coordinate and sequence activity. Additionally, timer and counter relays allow time and repetition-based functions to be incorporated into an electrically controlled system. We'll look at timers and counters and even solid-state relays with no moving parts in later lectures. Today's lecture deals exclusively with general-purpose electromechanical relays. Relays come in several forms, the two most common being the industrial or mini contactor relay, since it looks like a mini contactor, and the plug-in or IceCube relay, since it looks like an ice cube. IceCube relays come in many sizes, and it's a recommended practice to not put them in your drink. An IceCube relay has a matching keyed base into which the relay fits. The base is hardwired to the system, and the relay can be removed for inspection, maintenance, troubleshooting, or repair purposes. Sometimes plastic hooks lock the relay into the base and must be unhooked for the relay to be removed. Don't be the guy that rips a plug-in relay out of its socket and hears broken plastic pegs tumble into the equipment you're working on. The back of the bases typically clip into a rail. In contrast, an industrial relay is typically directly hardwired into the system. Just like the contactor, a relay is typically characterized by a set of moving contacts that make or break a connection when commanded to do so by an electrically isolated, low-power control signal provided to the coil. Sometimes these contacts are electrically isolated single-pole, single-throw switches, as is typical for an industrial mini contactor relay. Sometimes these contacts are single-pole double-throw switches, the shared common terminal, as is typical for an IceCube relay, sometimes called C-form contacts or transfer switches. Can you see why they're called C-form contacts? When one side is open, the other side is closed, and vice versa. Manufacturers sometimes use a single-pole double-throw switch symbol to make the transfer function readily apparent. This is the IEC schematic symbol for an IceCube relay. You can see the similarities. This is the coil. This is the common side for two single-pole double-throw switches. This is the normally closed side. This is the normally open side. The IEC schematic symbol makes it very clear the switches are controlled by the mechanical interlock with the coil. In either case, the switches are isolated from each other, and the switches are isolated from the coil. In its deactivated state, the normally open contacts are open and do not allow current flow, and the normally closed contacts are closed and do allow current flow. In their activated state, the normally open contacts close and allow current to flow, and normally closed contacts open and do not allow current to flow. A disclaimer before we continue. Always consult the manufacturer's datasheet for the specific relay of interest. Do not for a moment assume the pinouts and specifications presented herein are universal in nature. A thick, tangled jungle of not only NEMA and IEC differences, but also manufacturer-specific pin numbers and idiosyncrasies exist, especially for older relays. This being said, most manufacturers now offer dual NEMA and IEC numbering schemes, with the IEC numbering scheme becoming more and more accepted because of its standardization and ease of interpretation. The IEC terminal numbering scheme uses 2 digits. The first digit is the specific switch. For this schematic symbol of an industrial mini-contactor relay with 4 electrically isolated switches, 2 of them being normally open and 2 of them being normally closed, this is the first switch. Each terminal of this specific switch is assigned the first digit of 1. The second digits indicate the function of the switch. Normally closed switches are assigned a 1 and a 2. Normally open switches are assigned a 3 and a 4. Since this first switch is normally opened, these terminals will be 1, 3, 1, 4. This is the second switch associated with this relay. Each terminal of this specific switch is assigned 2 as a first digit. Since this second switch is normally closed, these terminals would be 2, 1 and 2, 2. This is the third switch associated with this relay. Each terminal of this specific switch is assigned a 3 as the first digit. Since this third switch is also normally closed, these terminals would be 3, 1 and 3, 2. Finally, this is the fourth switch associated with this relay. Each terminal of this specific switch is assigned a 4 as the first digit. Since this fourth switch is normally open, these terminals would be 4, 3 and 4, 4. Any auxiliary contact blocks added to this relay would continue this scheme starting at 5 for the first digit. IceCube relays with single-pole double-throw switches use a similar numbering scheme. The first digit is assigned the number of that particular switch. This is the first switch associated with this relay, so each terminal's first digit would be 1. The common terminal's second digit is 1. The second digit is indicative of a switch's deactivated state, similar to previously. A normally closed switch is assigned a 2 as a second digit. A normally open switch is assigned a 4 as a second digit. The terminals of the second switch associated with this relay would be assigned 2, 1 for the common, 2, 2 for the normally closed side, and 2, 4 for the normally open side. Alternate representations of the schematic would use the same terminal numbers. Any additional switches associated with this relay would continue in the same fashion, starting at 3 for the first digit. If you're ever lost about which pin is which, just look at the manufacturer's datasheet or on the side of the relay itself. Very often the pinouts are printed on the side as well as pertinent electrical data. Coils are normally designated A1 and A2. The coil is supplied the low voltage control signal, which could be 24 volts DC, 24 volts AC, or 120 volts AC as representative examples. DC coils with freewheeling diode arc suppressors are polarity dependent and must be connected with the correct polarity. If a plug-in IceCube relay has 2 coil terminals and 2 3-terminal single-pole double-throw switches, this means it has a total of 8 terminals. These are sometimes called octal base relays. Think octopus. Note the key on the plug and the socket and the dual numbering system. NEMA on the inside and the IEC on the outside. If this relay is inserted to the socket correctly, the 2 outside terminals on the bottom of the base are the 2 coil terminals A1 and A2, and the 2 middle terminals on the bottom of the base are the common terminals for the 2 independent switches 1, 1 and 2, 1. The 2 outside terminals on the top of the base are the normally open switches 1, 4 and 2, 4. The 2 inside terminals on the top of the base are the normally closed switches 1, 2 and 2, 2. Keep in mind we're looking at the base, not the bottom of the relay. If you look at the bottom of the relay, you've got to do a 180-degree switch on the vertical axis of the key. Other configurations exist. If we added another 3-terminal single-pole double-throw switch, this would be an 11-pin relay and obviously require a matching 11-pin base. The base for this specific 11-pin relay has the commons for all 3 switches on the row above the coil, the normally open terminals for all 3 switches on the row above the relay, and finally the normally closed terminals for all 3 switches on the top row. Note the dual numbering scheme is thankfully printed on the outside of the base. Additionally, tab-based IceCube relays exist. This is an 8-tab relay with an 11-tab base. This specific base has the commons for all 3 switches on the top row, the normally open terminals for all 3 switches on the middle row, and finally all the normally closed terminals for all 3 switches on the bottom row. Note the dual numbering scheme. Additionally, they're nice enough to explicitly print common, normally open, normally closed, and coil right on the base. If this 8-tab relay was used in this 11-tab base, the terminals for the middle switch 2 just wouldn't work. The state of the coil inside a relay is the determining factor whether a particular switch is in its deactivated or activated state. The coil is part of another electromechanical device known as a solenoid. A solenoid is an actuator, a term that means a device that takes one form of input and converts it into mechanical movement. In this case, the solenoid converts electrical energy of the control signal to linear mechanical movement via an armature. When the coil is energized by a low voltage control signal, the armature is pulled towards the coil and the contacts attached to the moving armature change from their deactivated to their activated or opposite state. One can see the actuation mechanism internal to an IceCube relay. When de-energized, the spring pulls back on the lever and the common in the center is making contact with a normally closed contact at the top and disconnected from the normally open contact at the bottom. When the coil is energized, it pulls the lever arm down and the common in the center is disconnected with the normally closed contact at the top and making contact with the normally open contact at the bottom. This is associated with a characteristic audible click that can be endearing or equally maddening depending upon the application. Solid-state relays, as we'll learn in later lectures, do not click because there's no moving parts to clack. One must disassemble a mini contactor relay to see the coil and armature. Upon cracking it open, we see something similar to the internal workings of a contactor. The base carries the stationary portion of the solenoid, the coil, and a pair of return springs that are maddeningly hard to properly realign when you reassemble the relay. Notice the shading ring. The coil is meant to be energized by 120 volts AC. The inductively linked shade ring keeps the armature engaged during zero crossing of the AC waveform and keeps audible hum to a minimum. The top portion contains the contacts, the contact carrier, and the armature. When de-energized, the return springs push the armature away. When energized, the coil pulls the armature into it and the associated contacts change states.